So good evening, everyone. It's really good to see so many of you coming into the session. So as you know, October is dedicated to quantitative methods in our research methods course. And I'm really happy that we have now a second visitor joining us tonight, Dr. Robert Duval Hernández, who is a colleague here at Open University, and he is in the School of Economics and Management. Robert is a labor economist, and he has graciously offered to join us tonight and talk about some really interesting, well, first of all, to share his perspective on research methodologies with us, but also to talk about some very current issues, not only in the social sciences, but I would say more generally for all of us who work with quantitative methods and analyses, particularly of large data sets. So Robert, welcome. We're really happy to have you with us tonight. And something that I'm not sure actually if you're all aware of is that, so Robert has prepared a presentation for us which looks extremely interesting. I'm really excited to hear this. He's entitled it Empirical Approaches in Social Sciences, the Case of the Credibility Revolution in Economics. And because actually both of us were really excited about this, particularly given the announcement last week of the Nobel Prize in Economics, we decided to, and you might have noticed an email to this effect from the OUC, from the University Press Office, that we actually invited other members of the research community to join us as well for the presentation part of tonight's class. I'm Dra Robert Duval Hernández, for those of you who don't know me, and we're very happy to have an invited speaker to our course tonight. Just to let you all know, the talk by Robert Duval Hernández is taking place in the context of the research methods course for doctoral students here at the Open University of Cyprus. So welcome to all of you. Let me just introduce you to our speaker, that we're very excited to welcome Robert tonight. So Robert is an assistant professor as well as the academic coordinator of the postgraduate program in management, technology, and quality. He's a faculty member in the School of Economic Sciences and Management here at OUC. And previous to joining the Open University of Cyprus, Robert served as an assistant professor of economics at CIDE in Mexico, a postdoctoral fellow at the Center for U.S.-Mexican Studies at UCSD, as well as visiting assistant professor and special scientist here at the University of Cyprus. In addition, he has been a consultant at the World Bank, as well as for research projects at the Inter-American Development Bank, the Mexican government, and for the United Nations University World Institute for Development Economics Research. He's currently an IZA research affiliate in Germany and an external affiliate at CIDE in Mexico. His research focuses on economic inequality and mobility, labor economics, and economic growth. So Robert, thank you so much for offering to speak with us tonight about this really current topic. Everyone, I would like to ask you to hold your questions for discussion until after the presentation. Robert has indicated that if you have any needs for clarification about anything, you can feel free to raise your hand or ask your question in the chat. So without further delay, Robert, the floor is yours.
Thank you very much, Jana, and thank you for the invitation to speak to our doctoral students, our incoming doctoral students, and also to the broader public that just joined us now in the framework of this course. So just to give you a little bit of overview, Jana had mentioned maybe I could give a talk about my own research to the doctoral students so that they could get a flavor of it. But I had thought that maybe it would be more interesting if I discuss recent methodological current that has taken place in economics in the last 20 to 25 years. I thought it could touch to many other people besides my specific area of analysis. And it so happened that after I had decided that, the Nobel Prize in Economics got awarded precisely to several of the researchers working on this area. So at that point, we decided, this might interest a broader audience than just the doctoral students. So here it is. This is the talk you're going to hear next, which it's called Empirical Approaches in Social Sciences, the Case of the Credibility Revolution in Economics. Okay. So essentially, I want to give you the talk is going to have 4 parts. First, I'm going to give you a very broad overview of empirical approaches that are used in economics. Then I will discuss the search for causal relationships in data as it's performed in economics. And I'm going to focus on this so-called credibility revolution that started occurring, as I said, in the last 25 years in economics, and it really has transformed the discipline to a great extent. And then I'm going to make more of a critical assessment of where we stand, what are the good things we have gained, and where are we lacking in further progress. Okay. So first, in terms of the overview of empirical approaches of economics, it's very hard, of course, to give an overview of this because, well, there are so many methodological tools open to us that it is easy to be on to certain methodological tools that are being used by economists. But I think that without being completely exhaustive, one could classify our empirical approaches or our methodological approaches to do empirical analysis within 4 broad umbrellas that you see in your screen right now. So the umbrellas would be, first there would be measurement and descriptive analysis. Then there would be model-based estimations. Then there would be estimations for the purpose of doing prediction. And then there would be causal empirical models. And within that framework, I will focus on the so-called credibility revolution, although they are not the only ones trying to answer causal questions. So let me talk a little bit about each one of these big 4 families or big 4 umbrellas that I have used as classificatory structure. So first, in terms of measurement and descriptive analysis, there is quite a lot of work in terms of economics for the proper measurement of variables that are of interest to us and that are of interest to the general public and for policymakers, variables as GDP, unemployment, inflation, inequality, trade flows, and so on and so forth. Now, there you might think, well, this is all settled. We know how to measure GDP. We know how to measure unemployment. We know how to measure all these variables. Why would it be that we care about this stuff? Well, the reason is that even if in principle we know how to measure this stuff, the simple fact that the economy keeps evolving creates new challenges for measurement of these key variables. Just to give you one example, we know more or less how to measure the production of an economy in a given year, which is GDP, right? But the fact that technological advances have become much more sophisticated in the recent decades have made the measurement, the traditional measurement of a variable such as GDP, much more complicated because it's much harder to measure the product of research and technology, which many times is intangible. Same goes, for instance, with trade flows. Now there is often trade in services, but it's not as simple to measure trade in services as it is to measure trade in goods. So in spite of the fact that we more or less know how to measure all these key variables, there is still a lot of research being done, both methodologically as well as empirically, to try to do better measurements as the economy evolves. Now, the second bullet point under this umbrella is descriptive analysis. And descriptive analysis here, it's a huge, huge umbrella, which I can only dump in there a bunch of empirical methods, most of which they have as a purpose to do what I would call confirmatory descriptive analysis. And what do I mean by that? I mean, we start from theories, from models of how the world works, how the economy works, or any social phenomenon work. And we go to data to see whether the predictions that my theory gives me conform to the data that I observe in practice. Okay, so it might not be that with the data I am exactly estimating all the parameters and all the characteristics that my theory is giving me, but it's a first approximation when these theories, sometimes they're actually quite complicated. I cannot do a full estimation of the theory, but I can go and do a descriptive analysis to see whether at least some of the key predictions are holding up in the data. And that is what I labeled, for the purpose of this talk, confirmatory descriptive analysis. But also by doing descriptive analysis, we are discovering new stylized facts to explain. So a lot of recent research comes from the fact that people go back and look at the old variables that we were used to look at them with new tools or from a new angle, and they start establishing some empirical regularities that then you try to compare with what theories predict, and then you come up with a new set of stylized facts that you want to create models to explain them. The second big umbrella is what I would call model-based estimations, and here I put two categories under this umbrella. I put calibration and I put structural models. I will talk later about structural models. The idea of model-based estimations is you start from a theory, you start from a model. Okay, in economics we are very keen mathematical models of the economy. So I gave you a flavor here. I'm not going to explain these equations that you see here. But you see, for instance, we have equations for how firms behave, how households behave, and how the government behaves, right? So we specify a behavioral model. Then some of these models, they have parameters that I need to know what they are. So I feed in, some of the parameters have been estimated by other researchers. So I just plug them into my model. And the rest of the parameters that I do not know, I take them to the data and I perform a calibration. And there are a host of techniques of what is considered calibration in order to find the values of my parameters in this model. I don't know, for instance, phi, rho, sigma, and so on and so forth, that best fit my data. Okay, and then once I have all the models, all the parameters in my model estimated, or I have a value for them assigned to them, I can start doing simulations. I was talking about simulation with one of our students at the beginning of the talk. We can do simulations. So for instance, we can simulate policy change in exchange rates, or simulate a change in taxes, okay? And then you can start playing what would happen with this toy economy that we have. Another of the big umbrellas that we have in economics is the umbrella of prediction through time series analysis, mainly through time series analysis. It's not the only tool we use, but mainly because it's very effective to do prediction is the use of time series analysis. Time series analysis is taking a bunch of variables that I call them here y1 to k, x1 to m, and take their current value and their past value and use them to predict the future values of one or more variables of interest. And time series is a set of tools that look at this variation between variables at a point in time, but also with itself over time, looking at the past to make predictions, and they have been very effective. Here, sometimes there are theoretical models that inform which model you use, but many times the goal has been, look, we are going to abandon the theoretical models and we are just going to look for the best prediction. And it has been quite effective, and a lot of policy done in the government, by central banks, by private firms, they do use time series analysis. I have to say, and I put it in red so that people doing time series analysis don't get angry at me, that of course time series analysis is also used for causal analysis. And I am not going to discuss that here because it's an entire topic for an entire presentation. I'm going to talk about a different branch of causal analysis. Machine learning, for instance, is also very good for doing prediction analysis of a different kind, but it's only slowly being adopted within economics. So we are still at the infancy of that in economics. So what I'm going to spend more time talking about is about causal empirical methods, methods that seek to uncover causal relationships from the data. So the problem is that if you start talking about causality, it's very hard to define. And if you look at the debates taking place in the philosophy literature or the epistemological literature, there is not a single accepted definition of what is causality. I give you, for instance, a few of the different definitions of causality. Causality could be regularity, theories based on regularity of events. Causality could be based on the how probable certain events are after something happened. There are the so-called counterfactual models of causality. There are the manipulationist models of causality, and so on and so forth. So I put this nice tweet by an epidemiologist who read, after summarizing on Twitter, a very interesting book by two philosophers on what causality is. The book is called Causation, a short introduction by Mumford and June. She concludes that, so what is a cause? My take home is that this is very hard. Philosophers have been debating for 2,000 years. And although most humans feel that they know what causation is and they can recognize it when they see it, it is not at all easy to put in words. And that is definitely the case. And I am not going to enter into these more philosophical debates, not only because it's not my area of expertise, but because it's an entire full area for research. What I'm going to talk about is more or less the model of causality that has taken a lot of impetus in economics as of lately, which is basically the counterfactual models of causality. So in economics, there is a lot of research being done using the counterfactual model of causalities, which in essence, it's a model about parallel universes. In other words, let me give you a simple example and you will understand what I mean by parallel universes. Suppose you have a subject. The subject could be an individual, a household, a country, a region, right? And that person, that I'm going to label it the person I, is going to be subject to some shock, okay? It's going to be, or to some treatment. So the treatment is going to be I'm going to call the treatment I. And just to keep things super simple here, I'm going to keep the treatment binary, just taking two values. By the way, can you see a little hand on your screen? I'm trying to see if the pointer works out. Can you see a little hand? Just type yes if you see a hand in the slides. Nope? Okay. So it doesn't work, this thing. Okay, so I'll just use a little pointer. Okay, fine. I'll use a pointer there. So I'm going to use a treatment, right, that is di here, that it can take values 0s and 1. What is this treatment? Well, for the time being, let's just think in terms of vaccinations as a treatment. So 1 if you took the vaccine for COVID, 0 if you didn't, right? The idea of counterfactual models is that for each treatment, there is a potential outcome, which is what would happen to some variable that you are interested in studying if you had been given the treatment, and what would happen if you were not given the treatment, okay? So there are two outcomes because my treatment variable only takes two values, 0 and 1. You got vaccinated or you didn't, right? And let's say that your potential outcome is not dying from COVID, right? So there are the outcome of, are you going to survive if you took the vaccine, or are you going to survive if you didn't take the vaccine? Of course, it is possible that you survive irrespectively of your vaccination status, but we conceive that some of you took the vaccine and you will have an outcome of survival in this world, but if you had not taken the vaccine in a parallel universe, there would be also a potential outcome that we don't get to observe, and that's the tough part. We don't get to observe whether you survived if you had not taken the vaccine. And the same goes for the unvaccinated. The unvaccinated, they will also have an outcome in this world that we will see in terms of survival, but in a parallel universe, there is also an unobserved outcome that we call the potential outcome of what would have happened to them had they taken the vaccine. And we do not observe them, we just observe what happened to you given the treatment that you got. So that's why we call about parallel universes. It's like creating a universe where I observe the outcome that I want to understand in a universe where you did not get the treatment, or you got the treatment opposite to what you got in this world. So let's start with a classic example in economics. The classic example in economics would be, what is the effect of an extra year of schooling on earnings, right? So we care whether education helps you get higher income. So here's a bunch of data for the United States many years ago. On the x-axis, you have schooling, years of schooling, completed years of schooling, and on the y-axis, you have wages. I put it in logarithmic form, but don't worry about that. Okay, and you have each dot here is an individual. So you more or less see that there is a positive relationship. And if you wanted to summarize it somehow, probably the easiest thing to do would be, let's keep it simple. Let's just take some averages. And that's exactly what I do in here. I take averages, and the red line that you see here joins the averages for each level of education. Okay? And you see that, as we expected, on average, there is a positive relationship between schooling and earnings. So it confirms our priors about that schooling causes you to have higher earnings. If you see this line, you actually see it's quite linear. It's a line that goes up and down, but it could be approximated by a straight line. So you could try to see, well, what would be the straight line that would best describe this positive relationship between income and education. So a straight line, we know it has two parameters. It has a constant b0 and it has a slope beta 1, right? And you could fit one method that is called linear regression that is ubiquitous in social sciences. We've been using it since the 19th century at least to find a good fit to that data. And if you do that, you actually see that it does a pretty good job in explaining the data. So the red line here is, again, the average log wage for each year of education. And the blue line here is the line that best fit the data. What do I mean by best? Just let me skip it because those are the statistical details, but they are really not important for now. Just say I have a method, I have a tool that allows me to do a good fit of that data. And it seems like the data pretty much fits a straight line like that. Of course, if I want to take my model to the real world, I need to remember that there are deviations from this line. So the red line here is the line that I fitted through linear regressions. But you see, I have differences for each individual from that line, and that I'm going to capture them with this red term that I'm labeling U, which is the error term, okay, which captures all those deviations, okay? So now the question is, very nice, I have a nice descriptive model of my relationship between education and schooling. Does that mean that's causal? And the answer is, of course, not. Why? Because we know that correlation is not causation, right? We know very well that, well, if correlation was causation, we would make the statement that you see on your screen. Birthdays are good for your health because studies have shown that people who have more birthdays, they live longer. So clearly, just finding a positive correlation between education and earnings is not enough to claim that I have uncovered a causal relationship between education and earnings. What is less appreciated, what everybody will tell you, even in discussions on the news, people will tell you, of course, correlation doesn't mean causation. What is less appreciated is that actually lack of correlation also does not mean lack of causation. And that's precisely one point I was discussing at the beginning of this talk with the PhD students. The fact that you go to the data and you don't find statistical associations doesn't mean that they are not causally related to one another. And to illustrate that, we have this very nice graph in here from a book on causality, where you would see if an external observer sees this sailor, sees the sailor is sailing along this straight path in spite of the fact that there are all these waves, and the extraterrestrial being comes and sees the sailor moving the rudder of the ship left and right, and he says, well, you know, I look that the rudder is moving left and right and is not changing the direction of the ship. And if you actually correlate the direction of the ship to the movements in the hand of the sailor, you will find no correlation. Yet, because we understand, we have a theoretical model of how sailing works, we know that, of course, the rudder causally determines the direction of the ship, and it's preventing the waves from taking you astray. But if we were just to look at correlation data, we would not be able, we could conclude that there is no causation between the movements of the hand of the sailor and the sailing direction, which would, of course, be wrong. So we need to be very careful about correlations, and in a way, regressions are more complicated than that. There is a comment by Mr. Potamos that, is it a connection between a correlation and a probabilistic method? Well, behind a correlation, there is built always a probabilistic model behind it. Yeah. Although at the end of the day, there are many probabilistic models that you could arrive. The correlation at the end of the day is a statistic, one of the many possible statistics we could build from different probabilistic models. Okay, let me skip this slide. What could go wrong then, in going back to my example of education and the causal effect of education on earnings? What could go wrong? Many things could go wrong, of course. I could give you an extensive list of what could go wrong with my previous estimations, but there are two big problems that we need to be careful. The first big problem is the problem of simultaneity. Namely, is not only that schooling can cause earnings, but also that earnings can cause schooling. So there is causality in two directions. And the other big problem is omitted variable bias. Namely, there are other factors besides schooling that affect earnings, but that are also related to schooling. So maybe the reason why I'm seeing a correlation between earnings and schooling is not because schooling is leading me to earn more, but is creating a spurious association because there are other hidden factors in the background creating this spurious correlation. So, of course, if we have more data, then we could refine our linear regression model, which is the first method I described you. In a way, a linear regression model is nothing but a glorified correlation, by adding other variables. So usually I observe something else besides earnings and something else besides education, and I can start controlling for other factors. Add new variables to my models. So I put my other variables, x2, x3, x4. Could be I add the gender of the individual, I add how many years of experience in the labor market it had, I add the industry where it worked. And by adding all these additional controls, what I'm doing is I'm going to estimate the effect of education of earnings comparing people that are alike. So I'm going to compare people that have the same level of experience, that are of the same gender, that work in the same industry. And then for these people, I'm going to be estimating the returns to education. And that's very neat. That's why this very neat property of multiple linear regression is why this tool is so popular in social sciences. The problem is that how can you be sure that all the that you included all the correct observable variables in your model? Surely there will be other factors that are going to remain hidden and that they will go into your unobserved term U here. For instance, in my example of education, there could be omitted factors such as motivation, right? If you're a very motivated individual, you will have a lot of education because you will study hard. But also when you go to the market, you will also earn a lot of money because that motivation will show up in your workplace. And that would create, even if you control for a bunch of variables, that would create a spurious association between education and earnings, because it's not coming up from greater schooling, but it's coming from the fact that it's driven by motivation, which I don't have a variable to measure it. Also connections, maybe you're very well connected and that allowed you to have good grades at school and study and go to college, but also when you came out, your dad had good connections and put you in a good job that paid a good salary, and that's why you have a positive association. So precisely because of that, it is hard to establish causality through our first method, which is the linear regression model. So we are going to be able to assert that we have found or established a causal relationship between a variable and an explanatory variable and an outcome variable only if the variation in this variable is what we call exogenous. What do I mean exogenous? I mean it changes. I observe in my data changes in this variable that are due to some external reasons that do not enter in the system that I am trying to explain. So in my system that I am trying to explain, I have individuals that are trying to make decisions about going to school, investing into schooling, right? And I can come up with a bunch of reasons such as labor market experience, ability, motivation, connections, and so on and so forth. If I can somehow come up with variation in my variables that is outside that model, outside that system, and that I can claim that it's an external variation that comes up as a shock, then I will be able to use linear regression for causal estimations. Otherwise, I will not. So here, let me give you another contemporary example where this problem might arise. Let's look to the problem of establishing what is the effect of vaccination on reducing mortality by COVID-19. So before jumping right into the model, let me just spend 1 minute talking about notation. First, we're going to have a treatment variable. And by the way, when you see treatment, I use the word treatment. That's just a variable that changes, the variable that I want to find the causal effect to. The fact that we call it treatment is because we are borrowing a lot of the language that medical sciences used. So we call it treatment, but treatment could be an extra year of education, right? So I'm going to have this treatment variable, which takes value 1 if you are vaccinated, 0 if you are not. My outcome is not dying from COVID-19. And it can take 2 values, 1 if you survive, 0 if you don't survive. Of course, by not dying, I just mean here literally not dying. It could be that either you didn't die from COVID because you got COVID and you survived, or it could be that you simply did not get COVID, okay? That's gonna be included into the outcome 1. Because I'm working with a counterfactual model of causality, that means I'm gonna have a potential outcome. So I'm going to have an outcome that for each individual in my society, what would be the potential outcome that I would have if I had got the vaccine, and what would be the potential outcome that I would have if I had not gotten the vaccine. But I'm only going to observe one of those, depending on whether I took the vaccine or not. And finally, I'm going to have the 2 ways of expressing probability, because I cannot make the statement for each individual. I'm just going to make average statements using probability statements. So I'm going to have the probability of not dying from COVID. I'm going to express it as P equal to Y equal to 1, the probability of not dying from COVID. And when I write PY equal to 1 / D, I just mean the probability of not dying from COVID, given that you got a treatment D. What is the treatment? Is either you got the vaccine, given that you got the vaccine, what is your probability of surviving? Or your probability of surviving, given that you did not get the vaccine. So having established that notation, let me then jump to what would be the objects that I might be interested in learning about in order to answer this causal question that you see here. So I can think of, on the top of my head, of 3 possible outcomes that would be of interest. The first outcome is the average treatment effect on the treated. That would be to what extent the vaccine increases your probability of survival for those that took the vaccine. Okay, so the treated is the people that took the vaccine, and I would like to know to what extent their probability of surviving COVID, either because they didn't get it or because they actually got it but they survived the disease, to what extent it increased because of taking the vaccine. Okay? I also would like to know to what extent the vaccine would increase the probability of surviving COVID for the people that did not take the vaccine. That's the average treatment effect on the untreated, right? And if I know these 2 treatment effects, the treatment effect, the effect of the vaccine for the guys that took the vaccine, and the effect of the potential imaginary effect of the vaccine for the guys that didn't take the vaccine, then I can build what is the effect of the vaccine for the whole population, because that just means averaging out these 2 quantities, right? I just take the effect on the vaccinated multiplied by the number of vaccinated guys, the effect on the unvaccinated, the counterfactual effect on the unvaccinated multiplied by the number of unvaccinated people, and I get the average treatment effect for the entire population. What is the problem? We are living in a counterfactual scenario because I cannot know the items that you see in red here. They are not known. Why? Let's go first with the vaccinated. For the vaccinated, I don't know what would be your probability of surviving COVID had you not taken the vaccine. Similarly, for the unvaccinated, I don't know what is your probability of surviving COVID had you taken the vaccine. So these are quantities that I would only get to know if I had a parallel universe where you got the opposite treatment to what you got in this world. But I don't have that. And since I don't have those quantities, that means I cannot estimate with observational data these treatment effects, neither one of the 3 treatment effects I just described. So what can we do? So all that I can estimate if I just took observational data, the fraction of people that survived COVID that had taken the vaccines is this quantity here. And I can compare that to the fraction that survived COVID among those who didn't take the vaccine. And I can take the difference of these, and I'm going to call this alpha, okay? But that number alpha is neither the treatment effect on the vaccinated nor the treatment effect on the unvaccinated. So it's none of the quantities that I care. And actually, that number alpha is going to be contaminated by what we call selection bias. And let me give you a simple hypothetical story that could overestimate the effect of the vaccine. So imagine that the people that selected and chose to get the vaccines are people that they are really, really, really afraid of the disease, and that in the counterfactual world, if you had not offered them the vaccines, they would have been ultra careful. They would have washed their hands 15 times a day, wore 2 masks, don't go to the supermarket, don't go to parties, and so on and so forth. So in that case, their counterfactual probability of surviving COVID, even if they had not taken the vaccine, this quantity here, the quantity in red in the first line, that quantity would still be moderately high because they would be taking a lot of precautions. Now, if the people that did not take the vaccine, on the other hand, they would be saying, look, you know, I want to live my life fully and I'm not going to change my habits because of a damn virus, maybe then they would also have the counterfactual probability of them. Then this probability would actually, the probability of surviving, given that you did not take the vaccine, might be actually lower. In the United States, I don't know if you know this, but in the United States, there were people, non-vaccinated people, that they were actually doing COVID parties to try to get COVID and just be done with the whole thing. So if you just focus on these 2 quantities that we have, that we can observe in the world, you're going to actually overestimate the effect of the vaccine. You're going to say, oh, the vaccine actually reduced your probability of dying from COVID drastically, but that's not really the effect of the vaccine. It's going to be a selection bias due to the fact that vaccination was voluntary and very different type of attitudes were displayed by people. And it's also possible to create a different story where you could find an underestimation of the effect of the vaccine, namely you would have a negative selection bias. So this number alpha that I can estimate with the data cannot be a reliable estimation of the causal effect of the vaccine as a treatment. So what can I do? And here comes method number 2. I can do a randomized controlled trial. I can do an experiment. In an experiment, as I said, what we need is to have external variation in my data. And the external variation in this example would come if an experimenter comes and say, we are not going to let people self-sort to who gets the vaccine and who doesn't. I'm going to randomly assign who gets the vaccine and who doesn't. And once you do that, then you really can estimate this causal effect, the average treatment on the treated, the average treatment on the untreated, and the average treatment effect. And in fact, that's exactly what the pharmaceutical companies did before taking out the vaccines on the market. They run randomized controlled trials, giving the vaccines to some people and giving a placebo to other people, completely random. The problem with RCTs is that they are expensive and sometimes they are unethical. Because you could not, for instance, if you want to learn the effect of education on schooling, you cannot say to someone that is ready to go to college, you cannot say, no, you know, I have a social scientist there at the building at OUC who wants to do an experiment on the effect of education, so you don't get to go to college. That's just simply unethical. You cannot do that. So RCTs, they are very nice because the experimenter can play around and create true exogenous variation, but the problem is that sometimes you cannot do that. So this is where the so-called methods of the credibility revolution come in. And I'm going to talk about 3 methods today. There are many others in tools, but I will not have time to get to them. I'm just going to talk about these 3 methods: instrumental variables, difference, indifference, and regression discontinuity designs. And the pictures you see here are the 3 economists, David Carr, Josh Angrist, and Guido Imbens, that got awarded the Nobel Prize a few weeks ago. And if life had been a little bit different, they would have been joined also by their co-author, Alan Kruger, who tragically died a few years before this prize came. Okay, so let me talk about the first of these methods. The method of instrumental variables is the method, the idea is try to find some exogenous factor that creates an external change in my treatment variable, in the variable that I want to study the effect of. So let's imagine that I have the diagram, this triangle that I have on the left. I have my treatment variable D, that I want to find the causal effect of D on my outcome variable Y, but I have some unobservable factors U that are lurking on the background and creating problems. And I cannot do experiments, and linear regressions are not good enough in this case. So in this case, the idea of instrumental variables is to find another variable, let's call it Z, right, which changes in this variable create changes in my treatment variable, D, and these changes are exogenous. They come from outside my system, it's like an exogenous shock that leads to changes in D, and they affect, as a result, my outcome variable Y because it affected D. So Z is not affected by the unobservable factors U that you see in the diagram, and it creates an exogenous source of variation. This method is actually very old. The idea doesn't come from the researchers I just showed you. It was created by a father and son, Philip and Sewell Wright, back in 1928 when they were trying to study, I think it was prices in some market. They developed this idea, so it's a very old idea in economics. But what the credibility revolutions and these researchers did was to scrutinize this method with more, putting a higher standard on what actually constitutes true exogenous variation, namely a good instrument. And let me give you an example of what it would be a good instrument in the frame of the question that I had asked before. So a good instrument, if I want to learn what is the effect of an extra year of schooling on earnings would be to use the quarter of birth, namely in which month of the year you were born. That is as exogenous as it can be because it's truly random in which month of the year we are born, right? So why that would help me to uncover this question? Well, it turns out that in the United States, in most states of the United States, you cannot leave school, or you are going to be subject to penalties, if you leave school before the age of 16 years of age. So you need to stay in school until you reach 16 years of age, and if you reach the age of 16, then you can decide whether you drop out of school or you continue studying. What this creates, this law, it creates that people that are born early in the year, say in January, their birthday, of course, comes in earlier than the people born in November or December. So if you're born in November or December, you're more likely to stay at school for longer than if you were born in January. If you go actually at the data, looking at the first graph on the left here, you actually see that this holds true. The blue line is how many years of education people born at the end of the year acquire versus how many years of education people born at the beginning of the year acquire. And it's always higher for the people born at the end of the year. But the month of the year is completely exogenous. So I have an exogenous variable that affects my treatment variable, namely schooling, years of schooling. And actually, if you go at the earnings data, you also observe that people born at the last months of the year, they also have higher earnings than people born in January. And it's not because they are smarter or anything, but it's truly because that affected how many years of schooling they acquired. So here is a very neat method created by Josh Angrist to find a true exogenous variable that would allow me to answer this question that I could not answer otherwise. In addition, the researchers, they have done research on how instrumental variables could be used when the returns to a treatment variable, for in this case schooling, are heterogeneous in the population. But for the interest of time, let me skip this application. In spite of being at the core of their prize, let me just skip this one and go to the next tool set. The next tool in the box is called difference indifference, and you can apply it when you have units, subjects that you can follow over time. And let me give you a nice historical example. In the 19th century, the city of London was ravaged several times by cholera. And back then, medical doctors, they had the theory that cholera was transmitted through miasmas which were floating in the air, more or less the way COVID is transmitted nowadays. Some doctors, however, were suspicious of that theory because there were several inconsistencies with that story, and they started suspecting that actually it was water the main channel of transmission of cholera. But they didn't have a good way to prove that, to establish that causal relationship between water transmission and cholera. One very smart doctor, Dr. John Snow, however, in his search for this causal relationship, had a very clever idea. He realized that the city of London, different neighborhoods in the city of London, they were getting their water source from different private companies. So here you have the blue water company and the red water company, and you see a map of the neighborhoods that were covered by these different companies, and you see the Thames River going in the middle. So this is the Thames here. And the interesting thing is that these water companies, both the blue and the red companies, they were getting their water from the Thames River, but also people were dumping their dirty water into the river. So cholera was exploding because once there would be an outbreak, the companies, they would get dirty water and send it to the households. So one fact of luck for Dr. Snow was that the red company here, the Lambeth company, decided in 1849 that they were going to change the source of where they were taking the water and go get water upstream in the Thames, further up in the river where people were not dumping water. And he saw that as an opportunity to test his theory. So what he did is, when he learned that the Lambeth company was going to change its source, at that year he went and he found out which households in London were getting water from the company, the red, and which ones were getting water from the blue company. But to make sure that these households were comparable, he limited his analysis to the households that were living where both companies were servicing, namely in the neighborhoods where there was an overlap between the companies. So they were socioeconomically more comparable. And he recorded, before the change of the water, he recorded the number of cases of cholera per 1,000 households. It turned out that the households being serviced by the red company, they had less cases than the ones by the blue company, right? But then he came back 5 years later and measured the difference in the cases. And it happened that for the household serviced by the red company that had changed its source of water upstream, the cases of cholera had actually fallen, and the cases of cholera for the blue company that kept getting the dirty water from the central London, the cases of cholera actually had gone up in 5 years. So he could estimate that, to take the difference between these two numbers and estimate that the fact of getting clean water led to 78 fewer deaths by cholera per 10,000 households. So this was a very clever way of using an exogenous source of variation to exploit data that changes over time. And this very clever idea has been applied now in economics to study many different questions, such as what happens when one place raises the minimum wage, another doesn't. But let me skip the other economic applications and jump to the last method that I wanted to showcase, that is at the heart of this methodological credibility revolution. The last method I want to showcase is the so-called regression discontinuity design. So the story of the regression discontinuity design, which by the way was a method devised in the 1960s by educational psychologists who wanted to learn about the effect of class sizes, is, suppose you have a variable that we call in these diagrams the running variable, okay? And you have that's going to be the variable that you want to find the causal effect of, and you have your outcome variable, that is the variable you are interested in. And suppose they are related, they are positively related, they could be negatively related, that's not material to the story. But for some reason, at some point in the running variable, there is a cutoff point. Namely, at some level of this variable, there are some thresholds. So usually these are actually effects of law. So for instance, the law says that you should not have classrooms that are larger than 30 students. And definitely if you are reaching classrooms with 25 pupils, you probably need to get a second helper for your classrooms. So when you have policies that create a breakup in the data, you can compare the people near the breakup, right after the breakup, and right before the breakup, and see whether there are differences in the average outcome that you want to measure, your y variable, between these variables, and that difference would actually be the causal effect of having that variable, but only around that neighborhood. Let me illustrate this with an example that is actually, I think, quite neat. Let's go back to the old question of whether vaccines reduce the probability of dying from COVID. In the UK, when the vaccination rollout started, they did it the same way that most countries did it, giving priority to the elder population. And it so happened that first they gave priority to the people 80 and up, but if you were less than 80, you could still get the vaccine, provided that there were remaining vaccines available or that you have a serious condition, right? So there were people younger than 80 that they were getting vaccinated, okay, but not that many. So the first graph shows you the probability of getting vaccinated related to your age. And you see a big jump after you cross the 80 years of age because people jumped to get the vaccine, okay? So you have here some policy externally imposed that created a breakup in the data. So what the researchers were interested in doing, these epidemiologists, was to see whether that created a causal effect of the vaccine on COVID mortality. And if you look at the mortality rate against age, of course they are positively related. The older you are, the more likely you are of dying of COVID, okay? But if you look around the neighborhood, say comparing the 80-year-olders with the 79-year-olders, you actually see here that there is a little jump downward here. Namely, the probability of dying of COVID was smaller for the 80-year-olders compared to the 79-year-olders. And there is nothing substantially different between the 80-year-olders and the 79-year-olders, other than the fact that the other got vaccinated more. So in spite of the fact that once the vaccination rollout started, you cannot do an experiment and mandate vaccines, here you have a clever way of using non-experimental data to tease out the causal effect of the vaccines on the probability of dying from COVID. And actually, if you look at the probability of dying from other diseases that are non-COVID by age, you don't see the breakup. There is a continuity between the 79-year-olders and the 80-year-olders, so you can be pretty certain that this jump downwards is because actually the vaccines were working. So I showcase you 3 methods, well, 5 methods. They all could be used to disentangle causal relationships, but not all of them can be used and some are more suitable in certain circumstances than in others. So let's take stock and discuss for the last couple of slides where we stand as a discipline. These methods, as I said, I give you examples both in epidemiology, medicine, and economics, but they have been widely adopted outside economics in other social sciences, especially in other sciences where you cannot run experiments. And they also have been widely adopted by industry. If you see the social media posts by Amazon, Google, Twitter, Facebook, and so on and so forth, they were all congratulating the laureates because actually they are working with them in using their methods and improving them to do new businesses, new analysis of the business data that they are generating. So what is the good that has come of this credibility revolution in economics? The good is that we have now a more solid set of tools to establish or to find evidence of causal relationships. Of course, as I said to the students before we started the formal talk, causal relationships, they start in our head. We start with a model, but if you want to go to the data to test whether that theory that you have actually holds, it is hard if you cannot run experiments. But what is good now is that we have a wide set of tools. I just touched upon a few of them that you can use with non-experimental data to find out causal relations. The second good thing is that, at least in economics, is that gone are the days of the kitchen sink approach to econometrics. And this is like an Americanism term that probably only Jana will understand what I mean by this. The kitchen sink approach is just throw everything but the kitchen. What we were doing in economics is, if you're going to do an analysis like regression analysis, people were just controlling for whatever number of variables you wanted and crossing their fingers to hope that that would actually uncover a causal relationship. And that actually is very poor practice. If you do a linear regression analysis the way I've done and many people have done, you actually need to think very hard what control variables you include and whether that can give you a causal relationship or not. So I think one of the best things to come out is that in social sciences or non-experimental sciences, we are really getting rid of these studies where you would just dump a bunch of variables and get some correlations there. What is also very good is that many of these methods I described to you, and I told you some of them they were centuries old, some were forgotten, they were rediscovered. But the important thing of this revolution is that these researchers, they brought these old methods and they created also new methods, that they put them in a new common causal framework, in a new common language to establish and to talk about causality. And it seems like a small thing, but it is not. Having a common language in which to express all these ideas about causality is actually very productive, because once you start seeing things in a common language, you start getting new ideas on how to improve a method to tackle more complicated problems. And actually, these methods, I gave you the simplest versions of them, of IVs, of regression discontinuity designs, of difference in difference. But they keep evolving constantly. For instance, the difference in difference literature, like the one with the river and the water, has had in economics an explosion of papers in the last year and a half to tackle more complicated situations where you have heterogeneity of effects between people and where people are getting treated at different points in time. So there is a fast-growing extensions to the original methods. And finally, the last thing is that descriptive studies still survive. I keep running, for instance, a lot of descriptive studies, but when we do descriptive studies, we are much more careful about them. So what is the bad then? Not everything is good. The bad is that, as you can figure out by the examples that I gave you, the evidence of causal relationships that is getting found in economics and in other social sciences is very piecemeal. Namely, we are finding, you need to find, if you cannot run an experiment, you need to find a clever so-called natural experiment. And sometimes there are no natural experiments, okay? Or if you find natural experiment, you have a natural experiment and you can identify the causal effect of one variable on another, but for a subset of the population that is not the one you're really interested in. So you have issues of external validity. How much can I generalize the effect of the vaccination that I found between the 80-year-olders and the 79-year-olders? Can I generalize that to the overall population, yes or not? Okay, so that remains a problem. And also the other problem is that there are many questions that they can just simply not be answered with these methods. So there are many aggregate policies questions, for instance, in macroeconomics, in environmental policies for global warming and so on and so forth, that cannot be simply tackled with these methods. You need a general model that allows for agents to interact and to affect one another. So to model, for instance, feedback effect. I think you cannot hear me. Can you hear me now? I'm getting some measures, some comments. Can you hear me? Yeah, okay, you can hear me. Very well. So when you have a system where there are interactions, so for instance, my neighbor gets treated with the vaccine and then I am encouraged to go take the vaccine, and there are these peer effects, these feedback effects, or when there are loops in the economy, in society, these methods might not work out because I'm working in a model where I have a parallel universe where my counterfactual outcome is already given irrespectively of whether my neighbor took the vaccine or not. So for several questions, I will not be able to answer, to use these methods to answer causal questions. Okay, so what are the challenges that lie ahead? And this is my last slide, my previous slide. We need to integrate these neat and clever ways of disentangling causal relationships with more theoretical, structural methods, with theoretical approaches, so that, and that's exactly what we call the structural approach to empirical analysis. And this is, there are steps being done in this direction, but there is much more that needs to be done. Also, when all these piecemeal evidence of causal effects here and there were being found, the answer, and people criticize them that, look, you know, this is very piecemeal, you are not finding the general effects that we want for the whole population. And the answer of the researchers were like, look, you know, it's better to have this piecemeal, and little by little we will know what the nature of the beast is. But here we don't have really a methodical way of learning the nature of the beast. And this reminds me of an Indian parable. There is this Indian parable where the Raja brings an elephant to find blind people, and tell them, describe this animal to me. So the blind people start approaching the animal. One holds the leg of the elephant and say, oh, the elephant is like a tree. The other touches the belly of the elephant and says, well, the elephant is like a wolf. Another one touches the tusk of the elephant and they say the elephant is like a sword. Another one touches the tail of the elephant and say the elephant is like a snake. And at the end of the day, they could not piece together what was the true nature of this animal that they had in front of them. And to a certain extent, that's a true challenge for people using these clever natural experiments, because we are getting pieces of causal evidence here and there, but we don't get the full picture of the elephant. Challenges ahead also is to include new methods such as machine learning, and there is a very active area of research now linking machine learning with causality. Just to close this, there is a nice anecdote. One of the people pushing this agenda in integrating causal analysis and machine learning is Susan Athey at Stanford University, who happens to be married to one of the Nobel laureates, to Guido Imbens. So the joke was, a running joke was that when the call from Stockholm came to the Imbens-Athey household, the kids pick up and say, oh, it's a call from Stockholm. And the question was, for who is the call? It's for mommy or it's for daddy? So in this occasion, the phone call was for daddy, but we are pretty sure that Susan Athey will also get a Nobel Prize a few years down the road, precisely because of this integration of machine learning and causal methods in economics. But this is at its infancy. And the last message I would like to leave you as I leave is that no single methodological approach will be key. There is not going to be a single approach that will be the best to answer causal questions. We need to be eclectic. We need to keep an eye open, because you might need different tools depending on the questions you want to tackle. And I'm going to stop here, not without leaving you, in case you are interested in learning about these methods, here are 4 books that are truly excellent. And also the summaries by the Nobel Foundation are very well written. And there are even YouTube videos by the Nobel laureates discussing these methods. I'm going to stop here and take questions because you were very quiet and I've been talking a lot. So you are welcome. So if anyone wants to open up the discussion, just open up your mic or raise your hand. Jana, you're the moderator. You set the rules.
Sure. Well, given that we're a small crowd here, well, yeah, maybe if you want to raise your hand, if you want to use your microphone to ask a question. By the way, some of the readings that Robert suggested, there are sample chapters. Actually, I think, if I'm not mistaken, the entire web version of the book is available. But there are links on eClass for the students to those too.
Yeah, both the book of Causal Inference by Scott Cunningham, this one here, and The Effect, they are freely available on the web. And they are truly excellent books. They are really The Effect is a little bit easier to start with, and also this one, Mastering Metrics by Nobel laureate Josh Angrist, is also easier. If you want something even simpler than this one, you can go to the YouTube videos here, and you can see Nobel laureate Josh Angrist holding a sword, samurai sword. So it's a little bit of a weird videos, but it's actually very clear and very good. But these are very good books. The hardest one probably is this one here, but they are very good books. Or read the summaries by the Nobel Foundation. They made a really good job in explaining these methods.
Well, if no one has a question, I'll ask one, Robert. So we talked a little bit with the students before your talk about being eclectic and appreciating different methods, and that there's no hierarchy in terms of which is better. And you ended kind of on a similar note that no single methodological approach will be king. But I wanted to ask you, isn't it still more or less the case that the controlled experiment, at least sort of in the eyes of the public, is sort of the quote-unquote best, most reliable thing, most credible thing to do? And I don't know, I guess does the domain of the research, well, clearly the domain of the research plays a role in the choice, because obviously if you're doing medical research, you'll want to do controlled experiments whenever you can. But yeah, I guess just what role does the public opinion play in all of this, if at all?
Yeah. Oh, no, that's an excellent question. And look, even in this field of research, many people, they call the randomized controlled trials the gold standard, because, so let me explain why it's the gold standard. The reason why it's the gold standard is because truly there the researcher can manipulate the causal variable that you want to affect, right? So yeah, in that sense, that's very nice. That's very neat. Where I think randomized controlled trials start running into problems is once you start putting them in practice. Randomized controlled trials might have a problem. The fact that it might be a gold standard in the terms of giving you exogenous variation at the hand of the researcher, but you still have problems of external validity. So you don't know if the experiment that you run is going to actually hold out in the population, right? So many of the experiments, you run it on a small sample because it's very costly and potentially ethically icy to do that. So you have the issue of external validity still holds. The issue of feedback effects that I mentioned in this slide and of aggregate policies, they also are very much in there. So even if you could run an experiment, so aggregate policies no, because you cannot experiment with a country, but the fact that if you make an intervention, say give the vaccines to my neighbor, and now I want to get the vaccine because I want to copy my neighbor, I don't want to stay behind, then the causality that you might turn, it starts getting complicated, because you really need to make sure that your subjects, they do not behave in a different way than the way the experiment is done. And one of the things, so we do experiments in economics. We do experiments usually, and I'm a little bit embarrassed to say this, but we do experiments mainly with two groups of people. We do experiments with poor people, with unemployed people, and with students, with three groups of people. Why? Because they are usually the people that accept to be part of an experiment. And one thing that we have learned is that experiments in practice, randomized controlled trials, they are very messy. People could change their behavior because of the trial in the most unsuspected ways, such that this nice example that I give you, that you make a randomized controlled trial and it's everything nice and clean, many times they don't affect. For instance, you cannot force people into an experiment. So at best, you will have some effects you will not be able to identify just by the sheer fact that you cannot force people into an experiment. And even in the medical sciences, experiments are complicated, because when the FDA does analysis, well, it's medical pharmaceuticals that do the analysis approved by the FDA, the Food and Drug Administration agency in the US that supervises all these medical trials. You find out that many of these experiments, they have a lot of contamination. Okay, so for instance, for several medicines, it had been found once the FDA started doing research that there were people that they were volunteering for a medical trial, and they were lying to the pharmaceutical companies and saying, oh, I want to be part of a medical trial. But they were going to another pharmaceutical company and say, I want to be part of a medical trial, because they were getting money in exchange to be part of that. So you can imagine if someone is getting a cocktail of 5 different medicines, one for heart disease, the other for liver disease, the other for coronavirus and so on and so forth, you're going to get a polluted sample. So experiments in practice, they still have the issues of external validity. They sometimes are impractical or too expensive or simply unethical. They cannot necessarily answer general equilibrium effects. And in practice, they are very, very messy. So if you can run a clean experiment and you don't violate any ethics rule and your experiment is clean, go ahead. It's truly great. And definitely I am grateful that there was a randomized control trial for the vaccines for COVID before they were open for the public. But I don't think that that's, I think that all these reasons make me doubt calling it the gold standard of empirical research.
Yeah, thank you for pointing all of that out. One thing that we've been talking about in the class, actually, it seems to come up again and again and again, and we're stressing it, of course, is that when it comes to doing empirical research, there are always limitations. And so that's why we have that little section whenever we write things up, limitations, and how does our interpretation of the studies, of the study that we've done, how is it impacted by these limitations? So thanks for pointing that out. I think we've got a comment on the chat from Janos. With the notion of parallel universe, you gave me an idea on how to tackle my research once I have results. Oh, that's terrific. Good.
I'm glad to help. I'm glad it helped. Really, I think, let me just say something about, I think another takeaway message, you were asking me before we started the talk, what would be my takeaway messages for the doctoral students. One, I said, keep an eye open for different methodologies, not tool is king, which we just discussed. The other one is always think of causality in terms of a theoretical model. You start from a model, then you go to the data. And that's where I go back to the diagrams that correlation doesn't mean causation, and lack of correlation doesn't mean lack of causation. But maybe the third one would be that I think you can gain a lot, we can all gain a lot, myself included, by even tasting a little bit of what are the epistemological debates among philosophers and epistemologists about what a cause is and how can you get at it with true data. Because only you start getting a torrent of ideas and see how complex it is. So even if we're not going to become philosophers ourselves, I think one of the disservices we do to our students is not to give them a closer roots on these epistemological debates. So if you can, PhD students that are listening this, or master students, because there are some of them that are master students, take your time and do some even light readings, introductory readings on this. It really pays off over time. And even for us, I mean, I still need to learn a lot about that as well.
Do we have any more questions for Robert? Or thoughts?
As we say in Greek, to zalizame. I think I got everybody dizzy. I talked too much.
No, it was a really interesting and accessible conversation, Robert. The fact that we meet in the evenings doesn't help, of course, because a lot of people come from work, other classes, so on and so forth. But it's also good that we've got the recording so that we can refresh at another time, and also that those who aren't able to be with us can see it.
Very well. So what do you say, Jana? Should we wrap it up?
Yeah, I think maybe we can call it a night. And thank you so much again, Robert, for joining us tonight. And yeah.
Actually, let me say one last thing for our students. I'll be more than, because I see Mr. Eleftheriou has posted another comment saying how he got some ideas here. If at any point in time, even if I am not in your program of study, but at any point in time you want to discuss these topics, just drop me an email. I'll be more than happy to make room to talk to you about any ideas that you might have, without interfering, of course, with what your advisor will say. No single methodological approach will be king, but your advisor's voice should come first, always.
Yes, indeed. That's really generous of you, Robert. Thank you. Thank you very much again. And I think this is a great thing that we've started by bringing in different faculty members so that the students have a chance to meet the colleagues, hear different perspectives and experiences. So I think it's really valuable. And frankly, it's super interesting for me too. So thank you very much.
Thank you for having me. Very well.